This is the last video in the series looking at reaction mechanisms for benzene. So we've got the nitration of benzene that we've previously looked at, we've done halogenation, and we've done acylation. Here we're going to look at the alkylation of benzene. So we're going to look at substituting an alkyl group such as a CH3, so a methyl group, ethyl group, or propyl group. We're looking to substitute for a hydrogen on a benzene ring. These reactions again are going to need a catalyst because the benzene ring is resistant to these types of reactions. So we are going to need a catalyst that offers an alternative pathway with a lower activation energy. So I'll do a simple example, just looking at the adding a methyl group or substituting a methyl group onto benzene. So what we will need for these reactions is a haloalkane. So we're looking at chloromethane here. We're going to use AlCl3 as the catalyst. We will produce an electrophile, and we will make AlCl4- for a brief time. Something I haven't mentioned in the rest of the videos is that the catalyst here, so the AlCl3 in the alkylation, the AlCl3 in the acylation, and the FeBr3 in the halogenation, they all need to be anhydrous. So it's important that they are anhydrous because all of those catalysts, both of them, the AlCl3 and the FeBr3, they react with water, and we don't want that to happen. So once we've produced this electrophile here, we can now look at the actual mechanism for its reaction with benzene. And again, the reactions are very, very similar. We are simply going to have an electrophilic substitution reaction where the benzene ring is broken as the electrophile approaches the pi electrons. So for a brief moment, the benzene ring will be broken in this horseshoe shape. I'll repeat again, this horseshoe should not go beyond carbons 2 and 6. The CH3 group is attached. The electrons bonding the hydrogen to the carbon will delocalize into the ring. The hydrogen will be removed as a proton, and methyl benzene will be produced. Along with the proton which has been released here. As with all the reactions, you need to show the reforming of the catalyst to show that aluminium chloride was acting as a catalyst in this reaction, and again we get fumes of HCl produced. So here you can see the full mechanism for this reaction. Just remember, as I didn't mention in previous videos, that anhydrous catalysts are used in these particular reaction mechanisms. What I haven't mentioned here in any of these mechanisms is the conditions, so you will need to be able to talk about whether they are under reflux. I've simply tried to focus on the mechanisms of the reactions.